So here I had two vectors and I wanted to write it as a linear combination. I wanted to express this as a linear combination of those things. In general, we will be working with a system like this. So I will have x and I will have beta, and y will be approximately equal to that. So I have got y and beta. These are vectors. And typically the sizes I will take n cross 1, and this will be n cross p, this will be p cross 1. So in my example, n is equal to 3, so there are 3 things, and p is equal to 2, there are 2 such vectors, and my beta, that is ab. So in my example, I have x given by these things. What are the things? 3, 4, 2. 3, 4, 2, and I have got 4, 1, 3. 4, 1, 3. So 3, 4, 2 and 4, 1, 3. So these are the vectors that I'll be. So this is the matrix that I'll be working with. Now instead of writing it like this with an approximate thing, most of the time we prefer to write it as this plus an error. We write it as vector epsilon, that is also n by 1. And this is the general form of a linear model. That's what we call a linear model. A linear model is just an approximate system of linear equation. Of course, later we are going to put certain assumptions on this epsilon, some statistical assumption. After all, it is linear statistical model, not just linear model. So we are going to put some statistical assumption, but more on that later. For the time being, how do we really find out the thing that I mentioned, namely that orthogonal projection? I just use the term orthogonal projection. By this I mean when you shine light perpendicularly on the screen, then wherever the shadow is, that is called the orthogonal projection. How you find that point? How do you find this particular vector? It turns out there is a nice way of doing that. Possibly you have already seen that in your linear algebra course. If not, don't worry about it. I will just tell you the technique. The technique goes like this. You will start with, let me just see. So you have this system, x, beta, approximately equal to y. Now what I will do is, I will just pre-multiply both the sides with x transpose, pretend that this is exact equality. Mysteriously, if you solve this system, the beta that you will get will give you the required solution. So this is called the normal system of equation, or normal equation. Now how do we get that is something we'll get into that later. It's a little bit of linear algebra. I do not want to get into that on the very first class. Now you might ask, what happens if this itself turns out to be inconsistent? Fortunately for us, this will be always consistent. Always consistent. Irrespective of what y you choose and what x you choose, this system is bound to be consistent. And if it so happens that this is non-singular, by the way, it's also a square system. You can see that this is a square system. It is p cross p, p cross 1, and this is p cross 1. So it's as many equations, as many unknowns. If this also happens to be non-singular, you are very happy. You will get beta equal to x transpose x inverse x y. And this is, of course, obtained from the data. This is part of the measurement, so we'll generally call it beta hat, in which case the solution is also unique. However, if this is not non-singular, then the system, I said it is always consistent, but may not have unique solution. We'll get into all those cases later. The simplest possible case is when it is non-singular, you can just find the unique estimator, and that is what is called the least squares estimator. Least squares estimator.